Hi everyone, I'm Latish, and today I will be presenting my real-time EV dashboard and advanced driver assistance system that I have developed during my Emertxe Embedded System internship. So the main objective of this project was to design and simulate an electric vehicle dashboard that can monitor important vehicle parameters in real time, while also implementing advanced driver assistance features such as collision warning, blind spot detection, overspeed warning, and high temperature monitoring. So in this presentation, I will explain the motivation behind this project, the system architecture, the implementation details, and the live demonstration. So now we'll see the internship overview. So this project was built as a part of MSc Embedded System internship. So during this process, I learned how to interface sensors, acquire analog sensors using ADC, configure timers, establish UART communication, and integrate multiple software modules into a complete embedded application. So our focus was on STM32. That is STM32 is used for the firmware development and peripheral configuration and debugging and all those things. Then embedded C is used to control the hardware peripherals directly. Then PiximLab it provides a simulation environment, and then the Python dashboard, the Python application receives the UR data and displays the vehicle parameters graphically. And then VSP creates a virtual serial communication channel between the simulator and the Python dashboard. So the problems statement like, so why are we doing this? What is the usage of this in real world? That is, we need a real-time EV monitoring system for the driver assistance and safety. Like we need a live visualization of all the vehicle telemetries. So what the solution here is that we monitor electric vehicle parameters such as vehicle speed, battery charge, motor temperature, and the surrounding obstacles continuously, and pass the values to the driver, which will help in making safe operating decisions. The ADAS continuously analyzes sensor information and warns the driver whenever a dangerous situation is detected. So therefore, the objective of this project is to integrate both an EV dashboard and ADAS into a real-time embedded system. So as we have seen, the project objective, that is to monitor speed, torque, that is the charge and temperature. They implement ADAS features like blind spot detection, collision warning, time to collision, etc., etc., and visualize this data using a Python dashboard. So next is about now that we already understood the motivation objectives of the project. Let us move to the hardware and software components that were used in this. So the primary hardware is of course the STM32 F103C86, which is also called the blue pill. Uh, then to simulate the driver inputs, 4 potentiometers were used. It is the connections were given as like PA1, PA2, PA3, and PA4, where the connection given to the 4 potentiometers. We'll see that by going to the STM32 by D. Initially, give a brief introduction. That is, the first potentiometer is connected to PA1, which simulates the acceleration pedal. Uh, like as the value increases, the speed also increases. The torque, power, all those increases. The second one is used for the brake pedal. That is increasing the brake decreases the vehicle speed. Also, it has an regenerative braking system, which will increase the battery state of charge as well using deceleration. And the third one is used to simulate the temperature. That is, it also helps to generate high temperature warnings if we monitor the temperature levels, which will help the driver in understanding if there's an issue and all those things. Then the last one is used for the battery, that is state of charge. It is used to initialize the battery percentage, and then the firmware updates and all those dynamically changes the SOC. And now set 3 ultrasonic sensors are used to monitor obstacles around the vehicle. That is three of them that is kept in front, left, and right. The front sensor for the collision warning, time to collision calculation, all those things. Left sensor for the left blind spot, and right sensor for the right blind spot. And then of course the software part, that is the STM32 ID, that is used for embedded C firmware, which I've already talked about. And PixSimLab, which is used to simulate the STM32 hardware environment. Then VSP, that is since PixSimLab this internal UART cannot directly communicate with the external applications, a VSP creates a virtual serial connection that allows Python dashboard to receive display values. And then these things like Python dashboard, all those things receives the UART data and displays vehicle parameters. That is what is given here. So this slide shows the complete overall the system architecture. That is potentiometer. That is the first stage. It takes the 4 potentiometers that simulate the driver inputs. That is the accelerator, brake, temperature, battery, and all those things. Then ultrasonic sensor. That is, we have seen 3 ultrasonic sensors are used to measure the distance of nearby obstacles. Then STM32. Like both the analog inputs and the ultrasonic sensor measurements are processed by the STM32 blue pill. Then the ADC then converts analog voltage to digital values. Then the vehicle logic, that is the firmware, then calculates all these values like speed, power, battery, SOC, motor temperature, driving mode, and all those things. Then after calculating the vehicle parameters, the ADAS module analyzes obstacle distances and operating condition. That is uh, collision, blind spot, or speed, high temperature, that fault, all those things are that is all those things are calculated and then this analyzed. And then the last, the UART is like all the processed information is transmitted through UART. Then VSP transfers UART data between the simulator and Python dashboard. And then the dashboard visualizes the Python dashboard, that is, it visualizes all vehicle parameters in real time. So this is how the configuration STM32 configuration we are given. We will see this in detail, and by going to the cube ID, I just posted the screenshot of this. That's it. The same thing about the PixSimLab setup as well. We'll see it in detail, and then about same code as well you will see. But I'll give a small introduction on what is that is. Instead of writing the entire code in a single file, we have divided the project into multiple software modules. So why we did this effect? It improves readability and efficient debugging. And this is the various modules we have used. That is main.c. Like main.c acts as the central control program. That is, it initializes all peripherals, GPIO, ADC, UART, timers, all that is used uh, in this internship, and all those are initialized in main.c. So then after initialization, the firmware continuously executes the main loop, and then the ADC is used to read all analog inputs from like the 4 potentiometers and all that. Then EV control, it is where we used to calculate the speed, torque, battery SOC, driving mode, the range estimation, motor temperature, and all those things. Then yeah, it also implements the regenerative braking. That is, the battery will increase slightly during braking. Then ultrasonic, that is uh, generates trigger pulses and using timers, I mean, measures echo pulse and all those using timers, and calculates the obstacle distance. Then ADAS, that is generate uh, safety warnings like collision warning, blind spot detection, or speed warning, high temperature warning, and fault conditions, all those things. This is the vehicle logic. That is three modes: eco, not sport modes are there, which will change. So you'll see how it changes by going to the code, and then it is a smooth acceleration and braking. That is, it won't just jump from a small value to high value as we move this uh, the potentiometer, which we will see later. But it will have a smooth acceleration, then power, torque, then dynamic association. That is, it will keep changing. It is not like a fixed value. It will change according to the conditions. The regenerative braking, that is, uh, the charge increases as we decelerate. I mean, we apply the brakes. Then dynamic motor temperature, that is, it increases as the vehicle keeps on going, like in a real-time system. Then this is about the communication, that is the STM32 sends through the UART at 115200 baud. Then the VSP creates a virtual serial connection between PixSimLab and the Python dashboard. The Python application continuously receives and updates the dashboard in real time. So why do we use VSP? Is that we have already told that is PixelLab internal UART cannot directly communicate with the external Python application. So it creates a virtual component allowing data exchange. So with this translating outcome, we will see after seeing the code and how it works and all those things. Before explaining the firmware, I would like to briefly explain this configuration. That is, you can see here, that is the first peripheral configured is ADC1. That is, ADC1 is used to continuously acquire the analog signals from the four potentiometers. That is, it's connected to PA0, PA1, PA2, and PA3. So I later explained, I think I explained as PA1, PA2, PA3, PA4. Sorry for that. It's connected to PA, not PA1, PA2, and PA3. It is PA0 is configured as an ADC input to simulate the acceleration pedal, PA1 for the brake, PA2 for the motor temperature, and for the state of charging, PA3. And then, I mean, this analog voltages are then converted to digital values. Then about the USART, that is USART1 is configured for communication 115200 baud, and then this is that this continuously transmits the processed vehicle parameters from the stability firmware to the Python dashboard through BSPE. And then DIM2 is configured as DIM2 is configured as a microsecond timer. Yeah, it's configured for microsecond timer, and that is, it is used for to accurately measure the echo pulse generated by the HCS9 that is the ultrasonic sensor. That this pulse width is then converted to the distance in centimeters, and those then DIM1. It is used for PWM generation. We can see it's available on the PA8 using channel 1, and then several GPIOs are configured. Like PC13 is configured for the as the trigger output for the front ultrasonic sensor. Then PB1 for the echo for the front ultrasonic sensor. Then PB2 for trigger output for left ultrasonic sensor. PB3 similarly for as the echo input for left ultrasonic sensor. And then additional GPI pins are configured for the right ultrasonic sensors using this trigger echo. And then after configuring the ADC GPIO timer USART peripherals, then after doing all this, we go to project and then build project. Sorry, project and generate code, and then the automatically it's all the peripherals initialization and all are handled using the HAL drivers. So now I will explain the code. So as you can see, See, instead of writing the entire application, I followed a modular programming approach. So the main source files here are main.c, adc manager.c, evcontrol.c, ultrasonic.c, and adas.c. So we'll first go to the main.c. So this is where all the peripherals such as GPIO, ADC, UART, timer are all initialized. So now go to while one. So in this loop, the the first one, the ADC manager update, that is it reads all analog inputs. Next is the ultrasonic update, that is it measures the obstacle distance. Next, EV update, that calculates the vehicle parameters. Now ADAS update, that is generates safety warnings. So ADC manager.c. So here so this module is responsible for reading all analog inputs from the potentiometer. So as we can see here, it reads acceleration, brake, and all those battery SOC and all those things, the motor temperature and all those things. So that is the code that is written here. Then EV control.c. So this is the module which implements the complete electric vehicle model, like speed, torque, power, battery SOC, motor temperature, range, driving model, and all those things. So here EV update function. So this function, EV update function, is executed repeatedly inside the main loop. You can see here the main.c, the while one we have called the EV update function. So all this accelerator, brake, all this code is written here. It is for example, like brake, that is the braking reduces the speed smoothly. Then regenerative braking, it is the code, it is written here, that is it increases, that is during braking the state of charge increases slightly. And then motor temperature code is also given here. And then finally the UART, that is all calculated values are transmitted through UART. Then these values are displayed in the both in the virtual terminal and in the Python dashboard. Now we will go to the next one, that is ultrasonic.c. So here also ultrasonic.c, see the read front one, that is it measures the distance from the ultrasonic sensor. What happens is that a short trigger pulse is generated, then the sensor returns an echo pulse, then the timer measures the pulse width, and then the pulse width is converted into distance. So that is what's given here. Then the same procedure is done for the left and the right sensors. Then ultrasonic update will be here. Then this function updates the latest the obstacle distances and all those things, and which are later used by the ADAS module. Now we are going to the ADAS one, that is this one implements all the advanced ADAS things, that is the advanced driver assistant features. Like here you can see the collision, a blind spot, over speed, high temperature, the fault code, and all these things. So yeah, this is the code. So now we will see the Pixel Lab simulation, that is first upload. We have uploaded. Now we can see the speed is 0, and I have now increased the speed. So you can see increase the acceleration. We can see the speed now getting increased. The same, the SOC, which was 100, now keeps on decreasing to 99. We can see the initial temperature was 39, but it's increased to 40 and 41 as the vehicle keeps on moving. And about the acceleration as well, the speed increases gradually instead of changing instantly, like real time. So next, we will see the braking system, and also along with that, once the speed is increased, the other values like power and the motor torque also increases. We can see the starting values, we can see the increase in the power and torque. So now we wait for some time so that the SOC decreases a little, so we can show the regenerative braking as well. About the braking, that is, as the brake input increases, the vehicle speed will decrease smoothly. Yes, it will increase. So I'll just show the braking now. Increase it. See, you can see the SOC changing. The speed also decreasing from 40 to 34. Again, 28 to 22. It's decreasing and it's decreasing gradually. So this is the uh, Pixim Lab simulation. Now we will see the Python dashboard. So now here is the Python dashboard. So try to so now the signal is also same. Okay. So now we'll put the values one by one. Now since the right side distance is being given very less, that's why we see the right side warning here. So now one should exist. Now we'll slowly increase the acceleration. You can see as we slowly increase the acceleration, the speed also gradually increases. You can see the range here. The range will also keep on decreasing. The SOC, that is 99. So as this recording progresses, we will see that decreasing as well. So the motor temperature is now at 27 degrees Celsius. So slowly increase that as well. Now you can see just 36 degree. And as this progresses, as the speed increases, the motor temperature also will automatically increase. Faster. So we have seen the right side warning. So we'll see the left side warning now. Say I decrease this. Now the left side warning should be, yeah. So now we can see a warning. Now about the front collision and all those things, you will see that now in this part. Now I just increase the speed so that once the speed, you can see the once the speed increases to I think 80 90 above, we will see this green color change to yellow, and above 140 I think it changes to red. We will see that. So for that I am increasing this acceleration, and we can see the time to collision changing. Now I will decrease it even more, keep it like this. So now the alarm is at none, but see now the alarm has changed to advisory. Now after some time we'll again make this speed maximum. So once it becomes critical, we will see the speed automatically decreasing. So now I will keep it at even lesser distance. So once it becomes critical, we can see the speed becoming 40, its speed decreasing. And now it becomes warning because the speed has decreased. It says automatic, like the decreasing speed, that system is also there once it comes close to the vehicle. So now we have seen, so we can see the fault as well changing 0 cross 04. So the speed history is also shown. Time to collision, the speed is being shown real time. And now the battery is at 96%. So what I will do is I will just decrease the acceleration a bit and increase the braking. So now you will see this change to 99 as a part of regenerative braking system. So yeah, that's about this Python dashboard. So now that we have seen the Python dashboard, we will now see the learning outcomes of this internship. That is, I learned how to write embedded C programs in HTML32, and I learned how to configure ADC, UART timers, all that in HTML32 IDE. I learned how UART communication is used to exchange data. I learned how to identify problems, isolate the root cause, and verify the solution. I overall gained technical knowledge and practical experience in this embedded systems development. And I would like to express my sincere gratitude to Emertxe and also to Jayalakshmi ma'am for her excellent guidance. Her sessions helped me understand both the theoretical concept and the practical implementation. So I would once again like to thank everyone involved in organizing this internship and help me improve my embedded system skills. So thank you very much, and I hope you enjoyed my presentation. Thank you.